I thank you all for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of June 2023. This question is from the section Algebra and from group theory in particular, and it is related to the symmetric group on n symbols, that is Sn. This question is from the part C, which is a multiple select question. There can be more than one answer, and the question carries 4.75 marks. The question ID is 704086. This question is suitable for all these examinations. Right. The given question is, let n greater than or equal to 1 be a positive integer and Sn the symmetric group on n symbols. Let delta be the set consisting of ordered pairs G, G, where G belongs to Sn. Which of the following statements are necessarily true? We are given four options. Option 1, the map F from Sn cross Sn. This is the direct product of two groups from Sn cross Sn to Sn, given by F of ordered pair A comma B is equal to AB, where A comma B belongs to Sn, is a group homomorphism. Option 2, delta is a subgroup of Sn cross Sn. Option 3, delta is a normal subgroup of Sn cross Sn. Option 4, delta is a normal subgroup of Sn cross Sn if n is a prime. Let us now discuss the solution of the problem in detail. We have a positive integer n greater than or equal to 1 and Sn the symmetric group on n symbols. Who are the elements of Sn? The permutations on n symbols. Right. The order of Sn is n factorial. Agreed. Now we have to discuss the truthness of the statement given in option 1. The map F from Sn cross Sn to Sn given by F of A comma B is equal to AB, where A belongs to Sn and B belongs to Sn, is a group homomorphism. First of all, note down, Sn is a group. Sn cross Sn is the direct product of two groups, is again a group, right? And from this group to Sn, a map is defined as F of A comma B. A comma B belongs to Sn cross Sn is equal to AB, the product AB. The product means the composition of these two permutations A and B as in Sn. And we have to prove that it is a group homomorphism. We have the map F from the group Sn cross Sn to Sn defined by F of A comma B is equal to AB. Now let A comma B belongs to Sn cross Sn and C comma D belongs to Sn cross Sn. These are any two elements of Sn cross Sn. Now for the homomorphism, we take F of A comma B compose C comma D. Right. Now how do we compose in Sn cross Sn? It is component wise multiplication. That is, AB multiplied by CD is AC comma BD. AC means A composed C as in Sn, BD means B composed D as in Sn. And f of the ordered pair AC comma BD by definition is AC BD. Right. That is the f of the product A comma B multiplied by C comma D in Sn cross Sn. Right. On the other hand, f of A comma B multiplied by f of CD, if we show that this is equal to the earlier one, for all A comma B, for all C comma D belongs to Sn cross Sn, then it will be a homomorphism. So on the other hand, f of A comma B is AB, f of C comma D is CD. So it is ABCD. So to be a homomorphism, these two must be equal. So f is a group homomorphism if and only if f of A comma B multiplied by C comma D as in Sn cross Sn is equal to f of A comma B multiplied by f of C comma D as in Sn. Agreed. Agreed. That means this is if and only if the first one is ABCD is equal to the second one is AB. First one is ACBD. This is ACBD is equal to ABCD. Now in a group, the cancellation laws holds good. So the left cancellation law you do, A will go away. The right cancellation you do, the D will go away. Thus you get CB is equal to BC for all BC belongs to Sn. Is it true? No. In Sn, when n greater than or equal to 3, it is a non-abelian group. Therefore, the product may not be equal. So this is not true in Sn when n greater than or equal to 3 because Sn is a non-abelian group for n greater than or equal to 3. If you are not satisfied, we will show you in this snippet. Now, let n is equal to 3. Let n is equal to 3. You take C to be 1, 2. This is a transposition. Is a cycle of length 2. B is equal to 2, 3. Cycle of length 2. Both are in Sn. S3. Both are in S3. Multiply them. CB is equal to 1, 2 multiplied by 2, 3. Compose 2, 3. Multiplication you do from right to left. 1 fixed, 1 goes to 2, 1 goes to 2. 2 goes to 3, 3 is fixed, 3 goes to 2, 2 goes to 1, it will come back to 1. So it is 1, 2, 3. In a similar fashion, BC is equal to 1, 3, 2. These two are not equal. So this is a counter example like thing. So what we have provided, therefore this is not true in general. So thus F is not a group homomorphism. So the option 1 is not true. Agreed. We move to the next slide for the option 2. So we have delta is the set of all ordered pairs G comma G. G belongs to Sn. Option 2. Delta is a subgroup of Sn cross Sn. Now take the definition of delta. It's very clear. The set of all ordered pairs G comma G. G belongs to Sn. Definitely. This will be a non-empty subset of Sn cross Sn. So it's non-empty. Why? Because there will be at least one G in Sn. Right? That is namely identity. You can take it. Agreed. Is a non-empty subset of Sn cross Sn, and to prove delta is a subgroup of Sn cross Sn, it is sufficient to prove that delta is closed. Why? Because Sn cross Sn is a finite group. In a finite group, to show delta is a subgroup of Sn cross Sn, it is sufficient if you prove that delta is closed under the operation that is present in Sn cross Sn. Right. So we take now G comma G belongs to delta, H comma H belongs to delta. Who are G and H? They are elements of Sn. Will multiply, compose them, G comma G, compose H comma H by the definition of the product in Sn cross Sn is component wise, GH, GH, they are equal. So GH comma GH also belongs to delta. So thus since GH belongs to Sn, for all GH belongs to, G comma H belongs to Sn. So thus delta is closed under the operation of Sn cross Sn. So therefore delta is a subgroup of Sn cross Sn. Thus option 2 is true. Right. We move to the next slide for the discussion of option 3 and 4. Right. We have option 3. Delta is a normal subgroup of Sn cross Sn. Option 4. Delta is a normal subgroup of Sn cross Sn if n is a prime. Is it so? What is true? What is false? So we'll first of all talk about normality. We have delta is a set of all ordered pairs G comma G, G belongs to Sn, and delta we have already seen it is a subgroup of Sn cross Sn. So we have to now only see the normality condition, that is G H G inverse belongs to H. For all G belongs to G, H belongs to capital H. That was the condition. So here appropriately you talk. Now you take for all X comma Y belongs to Sn cross Sn, and G comma G belongs to delta. We have X comma Y, compose G comma G, compose X comma Y inverse, G H G inverse, and that is equal to X comma Y multiplied, compose G comma G. Now X comma Y inverse in Sn cross Sn, what is the inverse of X comma Y? X inverse comma Y inverse. So XY, compose G comma G is apply composition XG YG component wise multiplied by composed by X inverse Y inverse. Again component wise composition, component wise multiplication XG X inverse comma YG Y inverse. So delta is a normal subgroup of Sn cross Sn if and only if xy G comma G xy inverse belongs to delta for all X comma Y belongs to Sn cross Sn and G comma G belongs to delta. Is it so? If and only if xg X inverse comma yg Y inverse belongs to delta. When this will belong to delta? If they are equal. What is the property of delta? G comma G, the entries must be equal. So this is if and only if xg X inverse is equal to yg Y inverse for all xy and G belongs to Sn. Is it so? Is it so? This is not true in general. Why? Take n is equal to 3. X is the transposition, that is the cycle of order 2, 1 comma 2. G is 2 comma 3. Y is 1 comma 3. All are transpositions, that is cycles of length 2. Now xg X inverse, that is X is 1 2 2 3. 1 2 inverse is 1 2 only. That is why 1 2 only. Now multiply. So you will get 1 goes to 2, 2 goes to 3, 3 fixed. So 1 goes to 3. 3 is fixed, 3 goes to 2, 2 goes to 1, it comes back to 1. 2 goes to 1, 2 goes to 1, 1 is fixed, 1 goes to 2, 2 is fixed. So 1 3. And yg Y inverse in a similar fashion you multiply, you will get 1 2. So xg X inverse is 1 3, yg Y inverse is 1 2. They are not equal. They are not equal. So therefore option 3 is not true. That is, it is not a normal subgroup. So the normality has gone. But in this example we have shown that it is a normal, not a normal subgroup when n is 3. What is 3? 3 is a prime. So in this example When n is 3 a prime also, it is not a normal subgroup. Therefore, option 4 is not true. Therefore, the answer to this question is only one, that is option 2. That is option 2. That is the detailed discussion of the solution of the problem from group theory, which is related to the symmetric group on n symbols, namely Sn. And it is definitely very elementary question. Very elementary question. So, it is a simple one. Anybody can answer this. I am sure that you have understood the solution of this problem. I thank you now for watching my video now. Please like my videos and share with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We hope to meet you once again in another episode of learning. Enjoy learning. I wish you all the best. Thank you.